In this lecture, we're going to talk about a more complicated divide and conquer algorithm to solve polynomial multiplication. So first, we'll talk about what polynomial multiplication is. So polynomial multiplication is basically just taking two polynomials and multiplying them together. It's used in a variety of ways in computer science. Error correcting codes. If you want to multiply large integers together, right? So if you've got 1,000-digit integers and you want to multiply them together, there's a quicker way than doing it the normal way you learned in elementary school. And that uses the idea of multiplying polynomials. It's used for generating functions, for convolution. Let's look at an example. So let's say you have polynomial A, which is 3x squared plus 2x plus 5, and polynomial B, which is 5x squared plus x plus 2. If you multiply them together, you get 15x to the fourth plus 13x cubed plus 33x squared plus 9x plus 10. Why is that? Well, let's look. For instance, the 15x to the fourth comes from multiplying 3x squared times 5x squared. That's 15x squared. The 10 comes from multiplying 5 by 2. The 13x cubed comes from 3x squared times x, which is 3x cubed, plus 2x times 5x squared, which is 10x cubed, for a total of 13x cubed. So let's look at the problem statement. So we're going to have two n-1 degree polynomials, right? A sub n-1 is the coefficient of the x to the n-1 all the way down to a0, which is the coefficient of the x to the 0 term, or the 1 term. And then we similarly have b polynomial as well. Now, first you may wonder, what happens if you actually want to multiply polynomials that don't happen to have the same degree? What if you want to multiply a degree 3 polynomial times a degree 2 polynomial, right? And where the degree is just the exponent of the highest term. Well, in that case, what you can do is just pad out the smaller polynomial, the lower degree polynomial, to have zeros for its earlier coefficients. I'll give you an example of that in just a second. And then the product polynomial is the result that we want to come up with. So that's a higher degree polynomial, right? If our incoming polynomials are of degree n-1, then we're going to get a term of the x to the n-1 in A times x to the n-1 in B, and that's going to give us an x to the 2n-2 in the C term. Right? So the c to the c sub 2n-2 term comes about from multiplying the a sub n-1 term and the b sub n-1 term. The c sub 2n-3 term comes from the a sub n-1, b sub n-2, and a sub n-2, b sub n-1. So it's got two terms that multiply together. The c sub 2n-4 term would have three terms that multiply together. And we have more and more terms that get multiplied and summed together, and then fewer and fewer back down. So c sub 2 has 3 pairs which get added together. C sub 1 has 2 pairs, and C sub 0 has 1 pair. So here's an example. This is actually the same example we had before. So n is 3, and all we need, notice, are the coefficients. We don't actually need to have the x's written out. So 3, 2, and 5 means 3x squared plus 2x plus 5. 5, 1, 2 means 5x squared plus x plus 2. What if b were only a degree 1 polynomial? It was just x plus 2. Well, then we would set b equal 0, 1, 2. That is, b's x squared term is 0x squared. Okay. So a of x is this, b of x is that. When we multiply them together, we get the same result we got before. And now we just pluck off the coefficients here. So the 15, the 13, the 33, the 9, and the 10. And that's our resulting answer, those coefficients. So let's look at a naive algorithm to solve this. Naive algorithm basically just says, well, first off, let's create a product array. This is basically going to be the C, the result. And it's going to be of highest degree 2n-2. So it's going to have 2n-1 terms, all the way from the 0 term up to the 2n-2 term. So we'll initialize it to 0, and then we'll have a nested for loop for I equals 0 to n-1, for j equals 0 to n-1, and at every time what we'll do is we will calculate a particular pair. So we'll calculate the a sub I, b sub j pair, multiply them together, and add them into the appropriate product. Right? Which is the appropriate product to put it in? It's the I plus j case. As an example, when I is 0 and j is 0, we calculate a at 0 times b at 0, and we add that to product at 0. So that says the two 0-degree terms in a and b get multiplied together to the 0-degree term in c. At the other extreme, if I is n minus 1 and j is n minus 1, we take a at n minus 1 times b at n minus 1, and we store that into product of 2n minus 2. As you can see, the intermediate values in product are going to have more terms added to them than the edges. And of course, then we return the product. How long does this take? Well, this takes order n squared. Clearly, we've got two for loops, one smaller for loop that's from 0 to 2n minus 2, so that's order n, and then a nested for loop where I goes from 0 to n minus 1, j goes from 0 to n minus 1, so those each go through the first one n times, the second one n squared times. So our runtime is order n squared. In the next video, we're going to look at a divide and conquer algorithm to solve this problem, although we'll see that it too will be somewhat naive.